So, valence bond theory is one of the theories of bonding. There are also Lewis bond, like the Lewis theory, which is when we draw the Lewis structures. And then the more complicated bonding theory after valence bond theory, this one's kind of in the middle, is molecular orbital theory. And we'll talk about that a little bit later. But for now, what is valence bond theory? It is when two orbitals overlap. That's really all it is. So here we see two unbonded, hydrogens by themselves, and then they get closer to each other and their orbitals overlap, right? Their s orbitals overlap. And now we have these electrons being shared, and now there's a bond there. There's a covalent bond there. Now, this specific overlapping of these s orbitals forms a sigma bond. Sigma is denoted by this Greek letter, which is sigma. It's the lowercase sigma, and that's what you get when you get two s orbitals overlapping. So on that same note, specifically this figure 1.10, you can see this overlapping again, right? Here we have this overlapping happening. So here we have two hydrogen atoms, right? Now they're too far away from each other. So the energy level is 0 right now because they're just not near each other. They don't have anything to do with each other. They're hanging out on their own. But when they start getting closer, they start overlapping. There's an ideal overlapping, right? And this is when it forms a bond. And this is a very specific bond length. Every bond has its own bond length. It can be shorter or longer than this. But notice that the energy is much lower at this level compared to having two hydrogen atoms by themselves. So this is more stable and ideal for these hydrogen atoms, right? They like having the noble gas configuration. But when you get them too close, the energy gets really high, and they actually, this doesn't work well, right? So this wouldn't actually happen. The energy required for this is way too high. So what happens is, ideally, it's at this length for the bond. And this is specifically, the term for this is called bond length. Now, on that same note of energy, right? So here we have two hydrogen atoms by themselves, represented by just orbital diagrams. You can see the energy level is much higher in comparison to the H2 molecule, which we just talked about. So this is the amount of energy released when the bond forms, or this is how much energy it takes when it breaks. And then this is the length of the bond. Now we're going to visit a simulation pretty quickly just to show you visually the two atoms overlapping. So this is the screen you'll see. You're going to see a pop-up just describing what the simulation is about. You can X that out, and now we can see what's going on here. So it's telling us to drag an atom's nucleus to explore bond formation. We have a hydrogen on the left and one on the right. And the overall interaction right now is attractive. We're moving one so that our orbitals can overlap. And you can see this potential energy decreasing, which is good, right? It means that it's releasing energy and it's probably forming a bond. And we kind of reached the lowest valley, which means that was probably the ideal length overlapping of these two orbitals, and now we're reaching that repulsive territory where they kind of don't like each other. Remember, electrons, they like their space. They will overlap. The orbitals of the electrons will overlap, but they need some space. So right here is balance. That's probably the best, but let's Let's make them go closer just so we can see that full graph. And here you can see it's actually giving me an error. So we went way too close, and you can see the potential energy is very high, meaning that's not really going to happen. We need that certain length where we get to that lowest energy. And that was just to show you overlapping of orbitals. This is what valence bond theory is about. So far, we've talked about like and like orbitals overlapping, right? We talked about s orbitals overlapping. But what happens when you get different types of orbitals overlapping, such as an s orbital and a p orbital, right? Right here we have an s orbital. These are the different p orbitals on different planes, right? 2py, 2pz, and 2px. What happens when all of these hybridize? What you end up getting is a hybrid version. They kind of just come together and they form a new type of orbital. Because we took the S, P, P, and P, right? That was 3 P's. It is now an sp3 orbital. This is the name of it, right? And because it's a total of 4 that we took, right? 1, 2, 3, 4, we have space for 4 bonds. So on its own, individually, this is an sp3 orbital. For a central atom with 4 bonds, it will have 4 sp3 bonds, and it will form a tetrahedral shape. So just to review, carbon has 4 valence electrons and forms 4 bonds. We know this already. In methane specifically, which is CH4, we know that it forms a tetrahedron. And when these hybridize together, these orbitals, we get 4 sp3 hybrid orbitals. Now, these hybrid orbitals on their own are unsymmetrical, but that's okay. But they do bond in a certain direction. So notice that the bigger lobe is always on the end, which makes sense. It gives more space for the electrons. Remember, electrons like their space. But why specifically into that shape? I actually kind of just talked about that. It's unsymmetrical, but this lets them overlap more effectively, gives the electrons their space, and as a result you get stronger bonds in comparison to just unhybridized s or p orbitals overlapping. So this is the methane. This is what we were just talking about. It forms a tetrahedron. We talked about this a few videos ago. And we talked about this representation, right? We have 1 hydrogen going to the back, 1 coming towards you out of the plane, and then 2 in the plane. Now, this is a tetrahedron, and the bond angle it forms, so the angle between the outer atoms is 109.5. And because you have only hydrogens around these carbons, this carbon, 1 carbon, all these bonds are equal. You can turn this compound around, you can flip it around, rotate it. It's going to be equal. Since all you have is hydrogens, everything's equal. All the bond angles are 109.5. All the bond lengths, so the bond length between the carbon and hydrogen is 109 picometers. What about when you have 2 carbons? So this is ethane. Don't worry about these names just yet. We will learn how these compounds are named and what the names tell you about the compound. For now, just know it's C2H6. This is the dot structure, the regular line bond, and this is a condensed version. So it's showing you the CH3 and then the CH3. You don't have to worry about that just yet. Just focus on that line bond. And what happens here is you need 4 spaces around each carbon. So what's going to happen is it's still going to hybridize into sp3, but this time it just happens to be that you have two carbons bonded to each other in the middle. Now, notice that the bond angle is a little bit different. It's not 109.5 specifically. These bond angles can change a little bit, but it's going to be around that area. And notice that this bond length here is different from the others. Remember, bond lengths are always unique. But here this is showing you two sp3 hybrid orbitals overlapping, the carbon and carbon, and this forms a sigma bond. And again, the smaller lobes, we're always focusing on the bigger lobe of the sp3 hybrid orbital, and the smaller lobes are just not shown, just so that it's not a big mess and it's more clear to you. So here we have a different example. This is now ethylene, right? Not ethane. And this compound is C2H4. And you notice that this right here is a double bond, not a single bond. Now, what we're focusing on here is we are learning that this is sp2 type orbitals that form around these central carbon atoms, right? We're always looking at the central carbon atom. The way we can look at this is we can look at the parking spots around the carbon. How many parking spots does this carbon need? 1, 2, 3. We need 3 spots. S orbitals, we know, is always just one orbital. It never has more than one. P orbitals, on the other hand, remember they have an X, a Y, and a Z configuration, orientation. So there's always 3 little parking spots labeled P, right? But we are only going to take what we need. And we said we need 1, 2, 3. So to form those 3, what's going to happen is these are going to come together. You're going to take that 1S and you're going to take 2 of the P's, right? So what you end up getting is an sp2 hybridized orbitals. Now, these angles are different, right? They're not the same as the sp3. Here we have, if we're looking at the carbon, one of these 2 central carbons, we have a 120 degree angle between these atoms. And let me erase some of this for clarity. So if we are looking at this carbon right here, this angle right here is 120, this one, this one. Those angles are 120 from the top. From the side, you have 90 degree angles. So if I was looking at this from the side, and we're gonna open up a simulation, so it'll be easier there to kind of visualize this. But we have 2 different bond angles here, 120 and 90, depending on how you're looking at the compound. Here, this is just showing you the types of orbitals, the ones that came together to hybridize. Remember, P and S, like I mentioned. What happens here is you have 2 different types of bond. For that double bond, we have a sigma bond and then a pi bond. So we have 1 sigma and 1 pi. That's how 2 bonds are able to form. So, and this caption right here just restates that. So we have 2 sp2 hybrid orbitals overlapping to form a sigma bond, and then we have empty unhybridized p orbitals right there. Those are the unhybridized ones, forming a bond, a pi bond specifically. So what if we add another bond to those 2 carbons, right? So what if we have a triple bond? What's going to happen then? Remember, you look at the carbon and you see how many parking spots it needs around it. It needs 1 and it needs 2. So all you need from our orbitals. This time you only need this one and this one, and they come together and they form sp, hybridized orbitals. These are oriented as the way that these compounds form their angles. It's to be for the bonding electrons and the lone pair electrons to be as far away as possible from each other. So the furthest away you can be from each other of two elements around this carbon is 180 degrees. So that's why you see that 180 degree angle right there. So the actual structure of this, again, shows that 180 degree angle because you have equal H's on each end. And notice that these bond lengths are unique again, 106 versus 120. And here we have a triple bond. So we have one pi bond there, one pi bond there, and a sigma bond there. And that's what forms that triple bond. One of those is sp and sp overlapping. This one right here is a pi, it's a pi bond, but it's a p, this one, that's unhybridized, overlapping with the other one. And the same thing with this one. It's a p overlapping with the p, those empty ones right there. So here is the simulation we used earlier. What you can do is open it up again, type in ethylene, type in ethane, start looking at them, kind of thinking about those bond angles, comparing our diagrams from our slides and chapter notes to those compounds that you're seeing show up. In the interest of time, I will give that to you as something to do on your own and to explore. It is linked here. And of course, let me know if you have any questions about